This lesson will explain the operation of the parking brake, and then we will look at the components that make up a typical hydraulic braking system. The brake kinetic energy graph will be described, as will the brake temperature indicating system. The parking brake is used to maintain pressure at the brakes when the aircraft is parked without chocks. Normally, once chocks are fitted, the brakes can be released. The parking brake is not a mechanical device such as is found on your car. It requires hydraulic power to apply and hold the brakes. The parking brake lever is spring-loaded to the off position. To apply the parking brake, the foot pedals are depressed. Then the parking brake lever is pulled. Whilst holding the lever in position, the pedals are then released. This allows the latch pin on the pedal mechanism to engage with the pawl on the lever mechanism, locking the pedals down and the lever in the engaged position, thus keeping the brake metering valves open, applying full pressure to the brakes. An electrical switch connected to the parking brake lever operates when the lever is in the engaged position, closing a valve in the anti-skid system return line, preventing fluid bleeding away from the brakes. A fully charged brake accumulator will have sufficient fluid to hold the brakes fully on overnight. To release the parking brake, the pedals are depressed, allowing the lock pin to release from the pawl and the lever to spring forward. The typical wheel brake system shown here has all the features and components we have discussed so far. The brakes are normally powered by one of the aircraft hydraulic power systems, System B, with automatic switchover to an alternate system, System A, in the event of low pressure in System B. When both normal and alternate brake hydraulic sources are unavailable, an accumulator will maintain pressure to the brake system. The accumulator pressure gauge is on the gas side of the accumulator. Provided hydraulic system pressure is available, it will read system pressure. However, if normal system pressure is lost and the brakes are operated, the accumulator pressure will fall until all fluid in it is used up. The gauge will then read the gas pre-charge pressure. The non-return valve will prevent backflow to the pumps. In some systems, the accumulator has sufficient fluid to stop the aircraft from high speed, but in others, it only has sufficient fluid to maintain the parking brake overnight. There are shuttle valves placed between the manual and auto brake systems. These will move across to allow whichever system is supplying the highest pressure to supply the brakes. The hydraulic fluid from the brake metering valves, or the auto brake valve, passes freely through the anti-skid valves to the brakes, unless an incipient skid is sensed by the anti-skid system. Wheel speed transducers mounted in the axles transmit wheel speed inputs to the anti-skid control unit. Each wheel is provided individually with anti-skid protection. When skidding is initially detected, the anti-skid controller adaptive pressure bias modulation circuit commands the respective anti-skid valve, firstly to release the brake pressure, then to apply a reduced pressure to protect the wheel from further skidding. Many aircraft have a system fitted whereby whenever the landing gear is selected up, the wheel brakes are automatically applied to stop the wheels rotating in the wheel wells. During the application of brakes, a considerable amount of energy is absorbed. This energy is released in the form of heat, which must be dissipated. The brake packs, wheel assemblies and tyres are capable of absorbing a certain amount of heat before they fail. Some method of determining the amount of energy absorbed will facilitate decisions regarding precautions and actions to be taken after an aborted takeoff, a landing, or simply taxiing the aircraft around the airfield. One such method is the brake kinetic energy graph. A graph similar to this one will be found in your particular aircraft performance manual. The graph is entered with all up weight and brake application speed in knots, corrected for wind, and then factored for the number of serviceable engine thrust reversers and airfield altitude. The graph will then indicate the amount of kinetic energy absorbed in millions of foot-pounds. This figure is not of much interest to pilots. However, the graph output is also split into 3 zones: the normal, caution and danger zones. It is these zones and the actions and precautions associated with them that the pilot is interested in. The actions and precautions for the 3 zones are listed here. You can take a moment to read them, but bear in mind that they will vary from aircraft type to aircraft type. As an example, we will use an aborted takeoff at a weight of 280,000 pounds, stopping from a speed of 125 knots, with no wind, and 1 reverser operating at an airfield with a pressure altitude of 2,000 feet. The graph is entered with the weight 280,000 pounds. We move across to the reference line, then up the guidelines until the 125 knot line is intercepted. We then move across to the reverser's reference line and up to intercept the 1 reverser operating point. We now move across to the altitude reference line, then up to intercept the 2,000 feet point. Finally, we move to the right to read off the brake kinetic energy absorbed, 27 million foot-pounds. As this was an aborted takeoff, Note 2 applies, meaning we need to add 5, which brings it to 32. So, we are in the danger zone. Many aircraft are fitted with brake temperature indicators. Older aircraft have electromechanical indicators, while on more modern aircraft, the temperatures can be displayed on one of the electronic display screens. Sensors are arranged to sample the temperature of the brakes of each individual wheel, and their output is sent to the indicator panel. Here, you can see a system typical of that used on many older aircraft. The indicator has 2 pointers labelled left and right. This particular aircraft has 4 wheels on each bogie. They are represented on the group of 4 mechanical push switches, only one of which can be depressed at a time. Each switch allows the brake temperature of a pair of wheels to be displayed on the indicator. For instance, if the left forward push button was pressed in, then the gauge would now be reading the temperature of the front pair of wheels on the left bogie. The brake temperatures of all wheels are constantly monitored by the system. If the temperature of any brake assembly rises above a predetermined level, then an amber high temperature indicator light illuminates. By cycling through the switch positions, the operator will be able to locate the wheel brake which is triggering the alarm. Should any brake temperature go even higher, there is another trigger point at which a red brake overheat caption will illuminate. On aircraft with a central warning system, the brake overheat warning will normally be repeated on it. There is a push button for testing the system. When it is pressed and held, the indicated temperature for the selected pair of wheels will rise by about 100 degrees. Shown here is the system used by Airbus. All of the landing gear information is brought together on one electronic screen. The brake temperatures normally appear in green, changing to amber with a caution light if the temperature exceeds 300 degrees Celsius. This system also has the facility to monitor the anti-skid system. The bars appear when the system is armed, and the release annunciations appear when the anti-skid is operating and releasing brake pressure. Brake temperature indicators are a useful guide for the crew. However, after heavy braking, in the event, for instance, of an aborted takeoff, it can take some considerable time, 10 minutes or more, before the energy absorbed by the wheel, tyre and brake assembly manifests itself on the temperature gauge. It is important that in such a case, the brake kinetic energy graph is consulted before a course of action is decided upon. There are a number of aids available to you, the pilot, to help you bring the aircraft to a safe stop on a limiting runway in marginal conditions. However, these all need to be used correctly. A safe stop begins with a good landing. This means using the correct approach speed and touching down at the correct place on the runway. Full anti-skid braking should be applied immediately after touchdown. Do not use cadence braking. That is to say, do not pump the brake pedal up and down. The ground spoilers should be immediately deployed, not so much for their stopping assistance, but more for the fact that they dump the lift from the wings, putting more weight on the wheels, allowing the brakes to operate more efficiently. Finally, reverse thrust should be selected without delay.